Hey everyone, in this video we're going to be talking about the Cartesian coordinate plane. We'll be talking about how to plot points, and once we are able to plot points, we're going to talk about the run and the rise between points, and then we're going to be talking about the distance between points, and we'll go over a couple of examples for those. So, to begin, let's take a look at the Cartesian coordinate plane. Okay, so there's quite a bit going on here, so let's take it one step at a time. So here we have the Cartesian coordinate plane. Now this came about in the 1600s. It was named after the philosopher, mathematician René Descartes. You may have heard the saying, "I think, therefore I am." That was René Descartes. That's the same man who invented the Cartesian coordinate plane. So if you take any philosophy courses, you'll probably come across that guy somewhere. But he's definitely one of my favorite mathematicians. He had a really interesting life too. So to begin, let's take a look at this Cartesian coordinate plane. Now, what it is it's a way to represent a particular point in space through the use of numbers. So if I wanted to signify a certain portion of, this screen here, I could represent this area with a set of numbers. Okay. Now what it is a number line here. We have the horizontal number line here. That's called the x-axis. And in parentheses, I also put input, because oftentimes the variables aren't necessarily called x and y. They could be called anything, but generally the input variable, whatever it happens to be, is put on the horizontal scale here. And now that's the one-dimensional line, and when we cross it perpendicularly with another line, in this case the y-axis, and in parentheses I also put the output here. So when we cross those two lines together, we get the Cartesian coordinate plane. Okay, and here I have a scaling set up. So what do I mean by that? Here we see that I'm counting on the x-axis by 1. So from the center here, by the way, this center is also called the origin. It represents the point 0, 0. But along my x-axis here, I am counting by ones. You'll see from the center here to here is 1, and then 2, and 3, 4, and 5. Okay. So you're going to want to set up some type of consistent scaling throughout your x-axis. And then you want to set up a scale for your y-axis as well. And it doesn't need to be the same scaling as your x-axis. However, you do need to be consistent with your spacing here. So from here to here, I call a distance of 1. So from here to here will also be a distance of 1, and so forth. So 1, 2, 3, 4, 5. Now in this case, I happen to have the same scaling set up for the x and y axis, but it doesn't matter too much. It really depends on the numbers that you happen to be working with. So now here we can see that there's 4 sections or 4 quadrants of the Cartesian coordinate plane. The top right is called quadrant 1, so the top right corner here is quadrant 1. Quadrant 1 is where the x variable is positive and the y variable is also positive. So if you're new to this notation, you have parentheses, your x variable would go here, and then comma, your y variable would go in the second spot. Okay. So this represents, quadrant 1 represents where x and y are both positive. Quadrant 2 represents the area where your x values are negative and your y values are positive. Quadrant 3 represents the area where your x values are negative and your y values are negative. So quadrant 3 is where both of your variables are taking negative values. And in quadrant 4, we see that, well, your x values would be positive, but your y values would be negative. Okay. So those are the 4 quadrants of the Cartesian coordinate plane. So I may refer to quadrants occasionally, so just know how those goes. Again, the top right is quadrant 1, and then you count counterclockwise. So top left is 2, bottom left is 3, bottom right is 4. So that's the Cartesian coordinate plane. Now what it represents is it's really a grid system. Okay, so let me put a grid here. So here I have a little grid here. I'll get rid of that in a moment because typically we don't fill in the whole Cartesian coordinate plane with a grid. We just we do the shortcut where we mark this off, and we could use our imagination where these lines will be crossing each other. But for now, let me put that back on. And let's take a look at plotting a few different points here. So let's plot some points. Okay. Alright, so I have 7 points here. Let's begin with this one, 2, 3. Now, the 2 here represents the position of your x variable, and the 3 represents the position of your y variable. So let me write that right here. So the first number represents your input. The second number represents the output. Okay. Oh, I messed up here too. I have the 2 circles, but just ignore that. Don't look over there on the left side of the screen. Let's stay over here in the Cartesian plane. So 2, 3. How do we do this? Well, first the 2 represents the position of your x of your x variable. So we begin in the center whenever we're plotting the point. We begin at the point 0, 0. Again, this is called the origin. So now we're going to move to the right 2 spaces. So 1, 2. So that's our x position. And now where is our y? Well, from here we have to go up 3. 1, 2, 3. Okay, and then we could plot our point right here. So 2, 3, it's where the x value of 2, that particular line here, this vertical line, and the y value of 3, this horizontal line, it's where those lines are crossing, and they are right here. So typically, again, we don't work with our grid, and it would look something like this. We just have to use our imagination here. So if we go over to the right 2, and then up 3, we plot the point there. Okay. So let me put the grid back on for now. Now we have the point 3, 0. So the x position is 3, and the y position is 0. Okay, so let's see how that looks. So again, we begin in the center. We move horizontally first. It's always the x direction first. In this case, we move 3. So 1, 2, 3. And by the way, that's 3 in the positive direction, right? And then the y position, it's at 0. Well, the y value of 0 is actually the x-axis right here. Essentially, what this coordinate is telling us to do is move right 0 and then don't move up or down any. Move right 3 and then don't move up or down any. So we're going to move right 3 and we stop here. We don't move up or down. We just plot our point. Okay. Now we have the point 0, 4. So we begin in the center. The 0 is telling us, okay, that's your horizontal movement. It's telling us not to move anywhere. It's 0. Okay, so we stay put right here. And then we move up 4. 1, 2, 3, 4. And we are right here. Okay. So let me go ahead and get rid of the grid. Let's not use that anymore. Typically, it's not something that we would draw out, unless you had graph paper or something like that. Then, that's convenient. So now, that's 0, 4. Now we have the point 3, negative 2. Well, where's that? So we're going to move right 3, 1, 2, 3, and then down 2, 1, 2, and my point would be right here. Okay, so we have 3 more. We have negative 1, negative 4. That means move left 1, and then down 4. So 1, 2, 3, 4, and we'd be right here. At this point, let me point out a fairly common mistake. Now, these coordinates here, these are x, y coordinates. Okay, we need both sets of directions to be able to plot our point. Okay, now this is representing a single point. It does not represent 2 points. So for example, this point 2, 3, it does not mean move right 2, plot a point, move up 3, plot another point. Okay, this is a very common mistake. Okay, you have to follow both directions first, and then you could plot your point. And it should just be a single point that you're plotting here. Okay, now let's go on to the next one, negative 5, 4. That means move left 5 because of the negative. 1, 2, 3, 4, 5. So we're sitting right here, right now. I'm not plotting anything, but that's where I am. And then we're going to move up 4. 1, 2, 3, 4. And should be about right there. Okay. And lastly, 0, 0. Where's 0, 0? Well, that's the origin. So that's directly in the center of our Cartesian coordinate plane. Okay. So that is how we plot points. If you're comfortable with that, that's great. If not, take a look back and take a look through these examples here. Once you're comfortable plotting, we can start to do some things with these points. Okay. The first thing we may want to do is talk about the run and the rise. And I know when a lot of people hear the term run and rise, they immediately think that these two terms are connected because of the slope. A lot of people have heard of slope before they get to this point even. So, however, run and rise have very specific meanings without the slope being involved. Okay, so run and rise have their own separate meanings, and I have their definitions right here. So for example, so the run, the rise is going to help us determine distances within our Cartesian coordinate plane, which is a fantastic thing to do. If you're marking locations off in space through numbers, if we can determine the distance between those points through numbers, it's going to be very advantageous. So we have the run here. The run is the horizontal transition from one point to another. And I have here an equal sign. X sub 2 minus X sub 1, or X sub 1 minus X sub 2. So what do I mean by that? Okay, let's see if I left myself enough room here to do this. Okay, so the run, if I'm given a point, so a coordinate 3, 1, and let's say negative 1, 3. No, negative 1, 4. Okay, so if I have this set of points here, we have 2 points. You could draw these in the Cartesian coordinate plane if you'd like. But this first set of points here, since I'm dealing with 2 points, I may want to have these labeled somehow. Now the first number represents our x value, right? So the 3 is an x value, and the -1 is an x value. Now since we're dealing with 2 points, I'm going to label this x sub 1, comma, y sub 1, and this one over here, I will label x sub 2, y sub 2. Okay, so that helps us differentiate these just a little bit. So now when we talk about the run, the horizontal transition from one point to another, we see that we could use, okay, x2 minus x1 or x1 minus x2. It doesn't matter at this point. Once we get into slope, then the direction could matter. Okay, but outside of slope, it doesn't matter too much. So here, the second x value here, let's do this, x2 minus x1 is equal to, now x2 is -1, and then we want to minus x1, which is 3. So -1 minus 3 is -4. Okay, so the run between these points here is -4. So if we take a look at the rise is the vertical transition from one point to another. Okay, so that for the run, it's horizontal transition, so the difference of the x values. With the rise, it's a vertical transition, so that's going to be the difference of the y values. Okay. Oh, by the way, if you did x1 minus x2, that would be 3 minus the -1, which is 4. Okay. So we get different signs, right? -4 or 4. It doesn't make a difference too much. Okay. If you do this like this, you'll get one version, and if you do it like this, you'll get the negative version of the first way. Same goes for the rise. So if we have the same points for the rise, okay, y2 minus y1, that's going to be 4 minus 1, which is 3. And if I do it the other way around, I should get -3. So that's going to be y1 minus y2 is equal to, that's 1 minus 4, which is -3. Okay, so let me go ahead and plot those points just so we could have a geometric picture of what we're talking about. And again, this is thanks to Rene Descartes. We could do this thing here. So we want to put arrows. And let me show you the bare essentials too. When you go to plot some points, let me show you what you need at the very least. So you want to label your axes. So this is going to be my x, and this is my y. Next thing you want to do is you want to scale your axes somehow. So we're dealing with fairly small numbers, right? So I'll just go ahead and count by ones. So here we have 1, 2, 3, and you want to label these. You want to label a few just so the person looking at your Cartesian plane knows what the scale is. So if you count like 1, 2, 3, they know the scale is 1. And similarly, that would be -1, -2, -3. And our y values are small too, so I'll just count by ones. 1, 2, 3, and 4. So let me scale that, and we could see the scaling is 1. And we have -2, -1, -2, and -3. Now this point 3, 1, that means move right 3 and up 1. So we plot right there. And -1, 4 means we move left 1 and up 4. So left 1, 1, 2, 3, 4, up here. So here's our 2 points. Now the run represents, again, the horizontal transition from one point to another. So The horizontal transition means this point is here, and it has to go 1, 2, 3, 4 to get to the same x value as this other point here. The height doesn't matter. The run doesn't care about the height. It really just matters how far to the left or right do you have to move to get to the other point. And that's what we had, right? We had a value of 4 or negative 4. Because if you're looking at from here to here, that's 1, 2, 3, 4 in the positive direction. If you're looking at this point to that point, that's 1, 2, 3, 4 in the negative direction. This is why we're getting positive or negative, and why it doesn't matter too much at this particular point. And now the rise, well, here we have a point here. Now, to get to the height of the other point, rise only cares about the vertical transition, not the horizontal. So we just need to move up until we're at the same height as the other point. So let's start at this point. We'd have to move up 1, 2, 3. And then we'd be at the same height. And that's what we expected, right? The rise should be 3. But if you're looking at this point and you wanted to get to the height of the other point, you'd have to move down 1, 2, 3. And that's where the negative 3 comes in. Okay, so that is the run and the rise. Again, these are their own concepts that, you know, they don't need slope really to be defined. I mean, they have their own definitions here. Okay, so that's run and rise. So if you're given 2 points, you know, you should be able to use these equations here or these equations here to find the run and the rise. Okay, and this is going to be really useful in later applications. And one application is coming up right here. So let's talk about the distance between points. So here I have the Cartesian coordinate plane. Here's my x-axis and my y-axis. And I have some sort of scaling going on here. You could tell I'm counting by ones on the x-axis, and I'm counting by ones on the y-axis as well. I have 2 points labeled. I have the point 0, comma, negative 3, which means you start in the center. You don't move left or right, but I move down 3. So the point is 0, negative 3. And I have another point here. I moved right 1, 2, 3, 4, 5, 6, and then up 1, 2, 3, and that's my point 6, 3. So now, what if I asked, what's the distance between these 2 points? Well, the distance between 2 points, you know, we're going to define it to be the shortest path between these 2 points in the plane. Okay, and in that case, it's going to be a straight line here. I mean, you could walk, you know, you could walk all over the place if you wanted to, but that's a waste. It's a waste of walking, right? Well, walking is good for you, though. You should walk. So the distance, though, we're going to find just, you know, from this point to this other point here. So we're going to go right there. Okay, so that's our distance. Now, how can we possibly find this? Well, let's try to find this distance making use of the run and the rise. So, the run, let's see, from this point here, the run would be going horizontal until I get to the x value of 6, right? So this is my run, and I know it's equal to 6, but we'll find that in a moment. Now, what is my rise? Well, my rise, let me draw the rise over here. My rise would be from there to there. Okay, so this would be my rise. Now this looks like a right triangle, right? That's because it is a right triangle. So here's our 90-degree angle here. The rise is one of the legs of the right triangle. The run is another leg of the right triangle. And then our hypotenuse happens to be the distance between these 2 points. So we know a formula. We could use the Pythagorean theorem. So you want to recall what this theorem says. It says when you have a right triangle, you can square one of the legs, add it to the square of the other leg, and it will equal the square of the hypotenuse. So let me call this distance here, let me call it d. Okay. So we know in our triangle here that the run squared plus the rise squared would equal d squared. Okay. Now, what is the run? Remember in the previous page, we defined the run to be the difference of the x values. So instead of writing run, let me write x2 minus x1 squared. And then for the rise, that was the difference between the y values. So y2 minus y1 squared. And this is equal to d squared. Okay. And lastly, we don't just want d squared here. We want just, we don't want d squared, we want d. So we're going to take the square root of both sides, which will eliminate the square from the d. Okay. Now you don't need to worry about this too much yet, because we didn't go over the equation solving. But here, let me write it down here. We're going to have x2 minus x1 squared plus the y2 minus y1 squared, the quantity of the sum underneath the square root, like that. Okay, and that's going to give us d. So we have to follow this formula here. Oops, and we will have the distance between the 2 points. So let's see. Well, let's let's do this in pieces here. So the run is x2 minus x1, which in this case is 0 minus 6, which is negative 6. Let me write it here, negative 6. Okay, and the rise is equal to the difference of the y's, y2 minus y1. And in this case, we have, I didn't tell you which one I was doing as x2 and x1, but I'm saying this one is x2 and this is y2, and I'm saying this is x1 and this is y1. Okay, so y2 minus y1 would be negative 3 minus 3, which is negative 6. Okay, so the run and the rise, we get negative 6. So now we have negative 6 squared plus negative 6 squared underneath the square root sign equal to d. So negative 6 squared is negative 6 times negative 6, which is 36. Same thing here, positive 36. And that's d. And lastly, we would do 36 plus 36 to get the square root of 72 equal to d. And we could reduce that to something called simple radical form, but we'll leave it as the square root of 72 for now. Okay, so that's our answer. And the important formulas here is this one here. Okay, so this is the the distance formula. Either that version or down here. Oops. Okay, so you'll want to have these at your disposal. So let's make use of that formula. Let's take a look at a few examples here. So find the distance between the points. Now, when you're trying to find distances between points and you're given the points, it's not necessary to plot these in the Cartesian plane. We can just go ahead and apply the formula to these points. Now, if you want to see what you're actually doing and why it works, you can refer to the Cartesian plane. You could plot these points. You could draw the hypotenuse. You could draw the legs of the triangle, which represent the run and the rise. And that's fine if you want a further understanding of this distance formula. But if you have the understanding already, we could just go straight to the formula. So if we want to find the distance between the points, we'll need the run. So the run is x2 minus x1. In this case, I'll say this is going to be negative 2 minus 3. So the difference of those x values. We get negative 5. And the rise is the difference of the y values. And in this case, this will be 4 minus 1, which is 3. Okay. So now, I know that if I take the square root of negative 5 squared plus 3 squared, this will be equal to d. Okay? So this would be the square root of negative 5 squared is 25, and 3 squared is 9. When we add these together, we get the square root of 34 equal to d. And that's fine. We could leave our answer just like that. Now, just as a reference, let me write the formula in the top right here. So the formula is, we have the run squared plus the rise squared. Inside that square root is equal to d. Okay, so refer to this if you have trouble remembering here. So now we have 2 points, negative 4, negative 3, and 1 comma negative 2. So again, we want to find the run, which is the difference of the x values. Now, I had mentioned that the direction that you subtract these numbers isn't going to make a difference in your final answer here. And one of the reasons it doesn't make a difference with the distance is because you're squaring the run and the rise. And when you square a number, you're always getting the positive answer. Okay, no matter if it's negative or positive, if you square it, you'll obtain a positive. So, it doesn't matter what you're getting or which direction you're going for the run and the rise. However, in the future, when the order does matter, you do want to start to be consistent in the way you define the run and the rise. So I've always just stuck to doing the second x value minus the first x value. And you should get used to that right now, I suppose, if you want. Which direction do you like? You like x2 minus x1, or do you like x1 minus x2? And go from there. Just take my word, it'll be beneficial for the future. So x2 minus x1, we have 1 minus a negative 4, which in this case is 5. And for the rise, this would be y2 minus y1. And I get negative 2 minus a negative 3. Okay, so that's the same as negative 2 plus 3, which is going to be positive 1. Okay, then I apply the formula. we're going to have 5 squared plus 1 squared underneath that square root, and that's going to equal d. That follows this formula here, the distance formula. And this is 25 plus 1 is 26. So the square root of 26 is equal to d. Okay, and last up, number 3, we have x2 minus x1, which would be negative 3 minus 3, which is equal to negative 6. And for the rise, we have y2 minus y1, and this is equal to 2 minus 2. So notice how in this case, 2 minus 2, we get 0. Now these 2 points here, they have the same y value, right? So it makes sense that the rise, the vertical transition between those 2 points should be 0, because they're already at the same height in the Cartesian coordinate plane. So we would expect a 0 there, that's fine. And then following the formula here, we'll have negative 6 squared plus 0 squared, and the square root of all that will equal d. And so negative 6 squared is positive 36, equal to d. And the square root of 36 is equal to 6. Okay, so d is equal to 6. Okay, so that is an introduction to the Cartesian coordinate plane. So it's an absolutely fantastic invention by one of my favorite mathematicians. So I hope you enjoyed this video, and I'll see you in the next one.